Welcome back. Today we're going to look at Mergesort, which is one of two classic sorting algorithms that are critical components in the world's computational infrastructure. We have a full scientific understanding of the properties of these algorithms, and they've been developed as practical system sorts and application sorts that have been heavily used over the past 50 years. In fact, Quicksort, which we'll consider next time, was honored as one of the top 10 algorithms of the 20th century in science and engineering. In this lecture, we're going to look at Mergesort, which is the basic sort in plenty of different programming systems, including Java. Next time, we'll look at Quicksort, which is also used in Java for different applications. All right, so basic Mergesort algorithm, what's it going to look like? The idea is very simple. What we're going to do is divide an array into two halves, recursively sort each of the halves, and then merge the result. That's the overview of Mergesort. It was actually one of the first non-trivial algorithms implemented on a computer. John von Neumann realized in the development of his EDVAC computer, one of the first general-purpose computers, that it was going to need a sorting method, and he came up with Mergesort. He's widely credited as being the inventor of Mergesort. So the idea of Mergesort is based on the idea of merging. And so to understand how merging works, we'll think about the idea of an abstract in-place merge. So we've got an array A, and its first half is sorted, and its second half is sorted. And the computation we need to perform is to replace that with the sorted array where those two subhalves are merged together. Let's look at a demo. The method that we're going to use is based on taking an auxiliary array to hold the data. This is one of the easiest ways to implement the merge. So the first thing we do is copy everything over to the auxiliary array. Now, once that's done, what we'll want to do is copy back to the original array, but get it in sorted order. In order to do that, we're going to maintain three indices. I, the current entry on the left half, J, the current entry on the right half, and K, the current entry in the sorted result. So the first thing we do is take the smaller of the two entries pointed to by I and J and compare those and take the smallest one and move that one to be the next item output. In whichever one is taken, we increment its pointer. Now we compare the minimum again. Again, the one pointed to by J is smaller, so we move that one to K, increment that pointer J, and also increment K. Now, there's two E's equal. We always take the first, so the one in the left array goes to K's position, and now we increment I and K. And again, it's an E, and they're equal, but we'll take the first one, so we move that one up, increment I and K. Now JZ is smaller than G. It's the next thing that has to go in the output, so we move that one up and increment J and K. Now the one pointed to by I, the G is smallest, so move that up, increment I and K. Move the M up, increment I and K. Now the last element in the left subarray is the one that's going to get moved next. And now that first subarray is exhausted, so really all we need to do is take the rest of the elements from the right part and move them back in. Actually, since we copied, we could optimize by avoiding these moves. That's an abstract in-place merge for taking the two sorted subhalves of an array, using an auxiliary array, move them out, and then put them back in sorted order. All right, so here's the code for merging, which is quite straightforward from the demo. We first, in order to sort an array of comparables. In this implementation, we pass a link to the auxiliary array in as well. And we have three arguments: low, mid, and high. So low is the first part of the array to be sorted. Mid's the midpoint that divides the first part from the second. So our conditions are that from low to mid is sorted, and from mid plus 1 to high is sorted. So the merge implementation, then the first thing it does is copy everything over to the auxiliary array. And then that sets up for this for loop that accomplishes the merge. We start our I pointer at the left part of the left half, the J pointer at the left part of the right half, that's mid plus 1, and we start the K pointer at the beginning low. And for every value of K, what we're most often doing is comparing whether aux of J is less than aux of I. And if it is, we move the element at J over in increment J. If it's greater, we move the element I over in increment I. And then in both cases, we increment A, and that increment K, and that implements the merge. If the I pointer is exhausted, then we just move over the J, next Jth element. If the J pointer is exhausted, we move over the next Ith element. So every time we're moving a new element into K, and that's the code that implements the abstract in-place merge. Now, with this code, we're also introducing the idea of making assertions just to make it easier to debug in our code and to have confidence that it's correct. In this case, this insertion just says we want to be sure that A of low to mid is sorted and that mid plus 1 to high is sorted before our code, and then we want to check that the whole thing is sorted after our code. And generally, Java programmers know that it's a good idea to try to do these assertions. Not only does it help detect bugs, but it also documents what the code is supposed to do, and that merge code is a good example of this. If you put at the beginning of the code what you expect in the form of an assertion, which is code itself, and you put at the end of the code what you think it's going to do, again in the form of an assertion, you're both testing that these conditions hold and also telling someone reading the code what you're trying to do with it. So Java is just an assert statement, and it takes a Boolean condition. In this case, we're using that method is sorted that we wrote before that returns true if the part of the array is sorted and false if it's not. And what assert will do is it'll throw an exception unless that condition is true. Now the thing about assertions in Java is that you can enable or disable them at runtime. And that's really important because it means that you can put them into your code to check while developing, but it doesn't incur any extra costs at all in production code. So by default, assertions are disabled. Something goes wrong, somebody analyzing the situation can enable insertions, and they often will help find out what the problem is. So the best practice is to use insertions just as we did in that example with merge, and to assume that they're not going to be there in production code. So you shouldn't use them for things like checking if the input is the way you like it. All right, so with that merge implementation, then the sort implementation is a quite simple recursive procedure shown here. So we use the merge procedure we just showed, and then our sort procedure is recursive, so checks that we have something to do first. Then it computes the value of the midpoint, same way as we did for binary search. Sort the first half, sort the second half, and then merge them together. And then the actual sort takes just the one argument of the array, creates the auxiliary array, and then uses that. Now it's important to not create the auxiliary array in the recursive routine, because that could lead to extensive cost of extra array creation. And you'll sometimes see merge sort performing poorly because of that bug. Otherwise, this is a very straightforward implementation, and it's actually a prototype for algorithm design that we'll see come up again and again. It's called divide and conquer. Solve a problem by dividing it into two halves, solving the two halves, and then putting the solutions together to get an appropriate answer. Here's a trace of what Mergesort does, and if you haven't studied a recursive program before, it's worthwhile studying this thing in some detail. This gives exactly what happens during each of the calls to merge. We start out with a big problem to solve, but we divide it in half, then we divide that one in half, and then we divide that one in half. And the very first thing that we actually do is just compare and exchange, if necessary, the first two elements. And then we do the same thing for the next two elements, then merge those two together to get the first four done. And then we do the same thing for the next four in the array. So now we have two sorted subarrays of size 4. We merge those together to get one of size 8. And then we do the same thing on the right, and eventually we have two 8s that we merge together to get the final result. Very instructive to study this trace to really understand what this recursive algorithm is doing. So now we can animate, and again, Mergesort's more efficient, so we can do more and more items. You can see it's got the first half sorted, now it's working on the second half. And then once it gets the second half sorted, then it's going to go ahead and merge them right together to get the sorted result. And it's got a little extra dynamics in the animation because of the auxiliary array. Let's look at it when it's in reverse order. Again, it gets the first half done, now it's working on the second half. Once it gets the second half done, then it goes ahead and merges together the whole thing. It's just as fast on reverse ordered as in arbitrary order. So you can run Mergesort on huge problems. It's a very efficient algorithm. And so, for example, what this table shows, if you were to try to use insertion sort for a huge file, say a file of 1 billion elements on your PC, it'd take a few centuries to finish. Even on a supercomputer, if you're using insertion sort, nowadays it'd maybe take a week or more. But if you have a good algorithm like Mergesort and you're trying to do 1 billion items, you can do it in just less than half an hour on your PC, and a supercomputer can do it in an instant. And smaller problems only take an instant even on your PC. So you can spend a lot of money or a lot of time, or you can use a good algorithm. And that's one of our main themes in this course. A good algorithm is much more effective than spending money or time, wasting money or time using a bad one. So let's look at the analysis of Mergesort. That's a bit of math, but very instructive because this really shows the power of the divide and conquer method and allow us to take a problem that was taking us quadratic time with methods like insertion and selection sort and get it done in n log n time with Mergesort. So that's the proposition. Mergesort uses at most n log n compares and 6 n log n array accesses to sort any array of size n. And the way to prove this proposition is to, from examining the code, to write down what's called a recurrence relation. And all that is, it's a mathematical reflection of what's going on in the code. If we're sorting n items, then let C of n denote the number of compares that we need to sort the n items. In order to get that done, we're sorting the left half and the right half. There's notation ceiling of n over 2 and floor of n over 2. That's the n over 2 round up, n over 2 round down. That's the size of the two subarrays. And we're going to call the same routine for that size, so the number of compares you need for that is C of n over 2. ceiling event over 2 for the left and floor event over 2 for the right. And then for the merge, we need at least, at most, n compares. If neither one exhausts, we need exactly n compares. And so, and that's true as long as n's bigger than 1. If there's only one thing, we're not doing any compares at all. So this is a mathematical formula that we derive by examining the code, but it completely describes mathematically an upper bound on the number of compares that are going to be needed. And similarly for the number of array accesses, if you count up the number of times you're accessing an array for a merge, it could be at most 6n. So these are mathematical formulas, and there's techniques for solving them, and we won't go into that. This is not a course in discrete mathematics. But what we can do is show how to solve the recurrence when n is a power of 2. And then it turns out that it holds for all n, which we can prove by induction from the recurrence. So if you have this recurrence, which is similar to the ones that we're talking about, it's exactly the same when n is a power of 2. Let's look at this one. If d of n is 2d of n over 2 plus n, with d of 1 equals 0, then d of n equals n log n. And we'll look at 3 proofs of that, just assuming that n is a power of 2. If n is a power of 2, then n over 2 is also a power of 2, so the recurrence makes sense. So this is just a graphical representation. If we want to compute d of n, we want to compute d of n over 2 twice. So that's 2. And then the extra cost for the merge is n. But if we're going to do this twice, then we have 2 n over 2s. Whoops. We have 2 n over 2s. And then for each one of these, we have divided into n over 4s, and each one of those 4 n over 4s has an extra cost for the merge of n over 4. Well, 2 over n over 2 is n, 4 n over 4 is n, and we keep going down and doing that till we get down to d of 2, and we always, for the extra cost of the merge, we have n. And how many stages do we have here? Well, it's the number of times you divide n by 2 to get down to 2. That's exactly log base 2 of n. So the grand total of all the costs for the merge, which is where the compares are, is log n times n, n log n. That's kind of a graphical proof, or a proof by picture, that that recurrence has that solution. Here's a little bit more mathematical one. We write the recurrence down, and then we divide both sides by n. So then it says d of n over n equals d of n over 2 over n over 2 plus 1. So it's dividing by n. So now this is a recurrence that telescopes. The first term on the right-hand side is exactly the same as the left-hand side, so we can apply the same formula. And all it does is divides by 2 again and then throws out another 1. And we keep doing that until we get down to d of 1, which is 0. And when we've done that, we've thrown out log n 1s. So we get d of n over n equals log n, or d of n equals n log n. That's another proof by expansion. Or using either one of those techniques, you can just get the idea that d of n is close to n log n, or you can write a program to expand the recurrence and find that. And then once we have the idea that d of n equals n log n, we can plug back into the original formula with the inductive hypothesis that d of n equals n log n. We want to show that d of 2n equals 2n log 2n. Using the recurrence, d of 2n equals 2d of n plus throughout the 2n, plugging in n log n, we get the desired result. You use this same idea on our initial recurrences for compares and array accesses to show that the number of compares and array accesses is proportional to n log n for merge sort. So that's the running time. Merge sort is fast. The other thing that we usually want to know is memory. And one of merge sort's characteristics is that in practical applications, it uses extra space proportional to n. That is, we need that extra auxiliary array for the last merge. We took two sorted subarrays and we talked about an abstract in-place merge, but we didn't have an actual in-place merge. We were using an extra subarray. So an in-place is important. A lot of times we're sorting everything we have. We want to fill up the memory with stuff to sort and then sort it. Insertion, selection, and shell sort were in place. They don't use much extra memory. But merge sort, you can only sort really half of what you can fit in memory because you need that auxiliary array for the other half. If you want, again, if you think that the things we're studying are easy, think about the idea of actually doing an in-place merge. People have come up with methods for getting this done, so it's theoretically possible, but the methods are generally too complex to be useful in practice, and they're not used. But there could be out there some easy way to do an in-place merge. That's another great algorithm waiting to be discovered. Now, there's a number of practical improvements that we can use to make merge sort even more efficient than the simple one that we've looked at. We'll take a look at those because they're examples of techniques that we can use for other algorithms. First thing is that merge sort is too complicated to use for tiny arrays. So say the subarrays are only of size 2 or 3 or 4. There's too much overhead with the recursive calls and so forth to get that done efficiently. And what's worse is the recursive nature of the sort definitely means that there's going to be lots of subarrays to be sorted. So one improvement that we can make is to use insertion sort and just cut off and use insertion sort, which is simple and efficient for small subarrays. So that's adding this one line of code to merge sort. We'll make it quite a bit faster, maybe 20% faster. A second improvement that we can make that'll improve the performance for cases when the array is partly sorted, this should just stop if it's already sorted. And that's going to happen in the case where the biggest element in the first half is less than or equal to the smallest item in the second half. That means it's done. So that's easy. We just put a test in the recursive merge sort for that to this one line of code to check whether we're done. That way, for example, if you were to call merge sort for an array that's already in order, it would just do this test every time, and it would be done in linear time. That's pretty helpful, although not totally helpful, but there's a lot of situations where that's helpful. The other thing that's possible to do, and it's a little mind-bending, so recommended only for experts, is to save a little bit of time. You don't really have to copy over into the auxiliary array. You can kind of switch the role of the input in the auxiliary array every time you make a recursive call. You still need that array, but you can set up the code in this way, which to sort an array, put the result in the other one. To merge an array, put the result back in the first one. So it's a recursive argument switchery to get the job done. And it's effective. It means you don't have to actually move items. And that saves a little bit of time. So here's a visualization of what the practical merge sort might look like. And this is with a big cutoff to small subfiles. So you get a visual feeling of how this sort gets the job done. It sorts the first little chunk and then the next little chunk and then merges those together and so forth and so on. A good visual representation of how merge sort gets its job done. That's the basic merge sort algorithm that we're going to look at different versions of next.